Okay, today we're going to do lesson 1.2, and I promise you there's a lot less terminology in this section as compared to the first section, and I think you'll find this section very easy to do. And I just want to point out, here's your study guide you're going to be doing. Don't forget to check the vocabulary words. If you need to, you can use your book again. A lot of the vocabulary words will come right from the book right here, and so use your book as a resource, and that should be fairly easy. Okay, so let's get to the lesson. So we're going to use segments and congruents together and learn about congruence today, 1.2. So our objective, students will be able to use postulates to identify congruent segments. And so the essential question is going to be, what are congruent segments? So I just want to go over a little terminology here. You won't have to memorize any of these rules. We will use these words several times, so you'll know them because of the repetition. In any event, geometry, a rule that is accepted without proof, is a postulate. And sometimes we'll call it an axiom, but that's more for like algebraic type rules. In geometry, we call it a postulate instead. On the other hand, if we do prove something, we call it a theorem. And so those are a couple new words, and we'll use postulate and theorem quite a bit in this course. So the ruler postulate, this is something we're just going to accept. We're not going to prove this in our class. What does it say? It says the points on a line can be matched 1 to 1 with the real number line. So basically this will allow us to measure the length of a segment, because every point on a segment can line up with some point that's on a ruler. And so that's kind of what we're going to do here. And so we have the real number that corresponds to the point is the coordinate. And here's a little picture of that. So you have the point here. This one we're going to call x1. That's the coordinate on the x-axis. And what we're going to do is something like this. Let me see if I can grab a ruler real quick. Tool right here. Tools. And grab this thing and see if I can grab a ruler here. Here's a ruler, and so what we do is we take those points and we line them up with a ruler. Like, for example, x1 is now lined up with 3 centimeters, and x2 looks like it's 8.7 or 8, something like that. So in any event, that's what we're allowed to do. We're allowed to place these coordinates onto a number line. And you know from algebra that you have the x-axis, which is the horizontal, and then you have the vertical axis, which you typically use y's. In this case, we're just looking at one dimension right now, and so we'll be basically using a ruler. So pretty easy stuff. Let me cancel. Let's go ahead and go now to, oh, hang on. I wanted to get this ruler out of here. Anyhow, let's move on. Got this ruler in there. How do I get rid of that? Okay, there we go. Get rid of that. Okay, so the ruler postulate continues here. It says the way we find the distance is just to subtract. What we do is subtract the coordinates. And we take this coordinate and subtract this one. Sometimes if you're on a number line, you might remember, let me just show you a number line real quick. If you're on a number line where you have x, well, you have 0 right here in the middle, and you have a number here, that might be -1. And if you have a point here that's might be, let's say, let's just call it -4. Okay, so let me get here. What we might have is point B being right here and point A being right here. And so if we were trying to find the distance AB, we would say the distance AB is equal to -1 minus a -4. Okay, and we use the absolute value so that if this number comes out as a negative, we would automatically make it a positive number, because distance only makes sense when it's a positive number. Well, in any event, here, let's carry this out. We've got -1 plus 4, because remember, in algebra, a negative of a negative makes it positive, and so then this would be equal to 3. So we would say the distance from A to B is equal to 3. Now, you'll notice something here. When we're talking about distances, there's no symbol on top. So no symbol on top means that we're talking about length. And remember from yesterday, we had several symbols. Let me just repeat them real quick. We had several symbols. We had A, B with a line symbol on top, and that would be this picture, you know, like that. You have A and B here. Okay. And then yesterday we also had segments AB, and so that would be this scenario where we have just this here. But segments have a symbol like that. And then we learned that, well, we could also have a ray AB. And so that would be this scenario where B is like here, A is here. And so that has a special symbol also. There's our generic symbol. And notice when we're talking about this one, it's equal to the length. Or, let's spell it, length or distance is what we're going to be talking about. So we would say like that length there might be 5, for example, and so we'd say the length of AB is 5. Well, so that's a little recap of what we were doing yesterday, and that's what we're going to be doing here. We want the length to always be positive, and so that's why we take the absolute value. Okay, so let's continue. Alright. So, applying the ruler postulate, we can find the length of segments. You'll notice this is looking like it's 5.4. Okay, this length here is 2. So we simply subtract those two and take the absolute value. And we get 3.4 in this case. Pretty easy. So, some problems in this homework, it's pretty easy. One of the things we need to realize when we're going to be adding or subtracting is whether a point is between the other two. So this idea here, between. So if you have a line, oh my goodness, like imagine my line is straight. If A is here and B is here, then this point C right here, we would say is between the other two. Let me ask you a question though. If I put the point here instead, is C between A and B? Well, we would say no, because one of the things we're going to insist is that the points are all collinear. So they all have to lie on the same line to begin with. So anyhow, the point could be over here, that's between. If C is right here, that's okay. If C is over here, then C is no longer in between A and B. So be careful. Don't get this confused. But we need this idea before we create the segment addition. Whoa, let me back up. Sorry. So, reviewing here, we have B is between A and C. E is not. Okay. Well, that's kind of what I covered on the previous little diagrams I was drawing anyway. So, okay, well, now we have a rule. And we call it the segment addition postulate. It's pretty straightforward. It basically says if you add this part and you add this part, it equals the total. It's like, duh. It's almost like, well, let me just give you a quick example. If this is 8 and this is 2, then what can you say? Well, we could say that the total length is 10. It's that simple. And so you will have some easy problems on this assignment. I don't think you'll find it terribly challenging. But here's the thing. In order to use this postulate, you need to have a point between A and B. And we'll call that point C. Or in this case, B is between A and C. You need a point between the other 2 points. Okay. So we can use this with maps all the time. In this problem, we want to find the distance. Use the distances to find the distance from Lubbock, I'm not sure how to say that, Lubbock, Texas to St. Louis, Missouri. Well, we know the distance from Lubbock to Tulsa, and we know the distance from Tulsa to St. Louis, so basically the segment addition postulate says, hey, you know what, you can add those two. So we could just take 380 and we can add that to 360 and we can get the total. Now that's kind of hideous. I'm going to change colors. Wow. So what do we get? 14, carry the 1, 740. And this would be, the total distance would be in miles, right? 740 miles. That was a pretty bad circle. There we go, that's better. 740 miles. So that's what the segment addition postulate says. It's pretty easy. Sometimes though we have algebra problems, so it won't always be that easy. And sometimes you'll be asked to use a ruler. Since we're doing inches here, let me show you how we could do that. You want to go to the nearest eighth of an inch, and maybe you're not familiar with the ruler, so I'll just use one real quick. Bring up my ruler real quick. There it is. Oh, that's odd. I only have centimeters and meters. Well, let's go. No. Well, that's a bummer. Well, anyhow, if we were using, here's the inches on this side here, so that works. So the point is, we could set one of the points up here on the 0 inch, and we just measure out this way. And it looks like to me it's 3.5 inches. The nearest eighth, though, the nearest eighth, or, well, let me use my pen here. The nearest, there's an eighth right there, there's an eighth, there's an eighth right there. And so these smaller portions are 1/16ths. So the next line up is an eighth. So again, this would be 3, looks like 1/8, 2/8, 3/8, 4/8, which is pretty close to where we're at. I mean, that pretty matches up there. So we would say this is 3 4/8, and of course 4/8 is actually 3.5. So hopefully that makes sense. 3.5 inches. Well, so anyhow, that's not terribly hard. You could all use a ruler, I hope, and Anyhow, I want to put this away now, so I'll click that off of there. Go back. Oh, what about that one? I guess I could get my ruler back. I'm going to measure that to the nearest eighth. So then my ruler. Oh, goodness, has the inches on here. So probably the easiest way is just to place one of the points at 0. And what do we get this time? It looks like to me 2 1/8. This would be right there. 2 2/8, 3/8, 4/8, 5/8, 6/8. Looks like to me it's pretty close to 7/8. So I'm going to say 2 7/8 inch. Okay, so that's pretty easy. So you might need a ruler. Hopefully you have one at home. I have some in class. If you need to borrow one, just come on up and let me give it to you for class time anyways. Okay, well now try this problem. This problem is almost the same as the previous one, but this time what we have the total distance. The total distance being right here. We have this distance from here to here. We don't know this distance. So if you don't know something, we can just put x right there. And so what we could say using the segment addition is that 99 plus x is equal to the total distance, 289. And now if you just use a simple calculator, or you might be able to just do this one in your head. If you subtract 99 on both sides of the equal sign, you get x is equal to 288. Wow. Pretty smart. And of course this is in terms of miles. Okay? So sometimes you have to do some subtraction problems. But not too hard yet, right? Everybody hopefully can do that sort of algebra on your homework. Anyhow, let's continue. Nothing too terribly hard yet. So maybe you'd like to try this now. This time you're not supposed to use a ruler. In fact, if you use one, you're going to say, well, hey, that doesn't match up right. Well, you're supposed to use the segment addition postulate. Okay, so once again, what you can do is you can call this one x right here. You can say this one plus this one equals 36, and you can solve for x. I'll give you about another 30 seconds to solve that. Shouldn't be too hard. Okay, so if you write out the equation, we'd have 21 plus x equals 36. And once again, we subtract on this side, we subtract on this side. Real simple, easy algebraic equation. This x drops down this way. So we get x is equal to, what do we get, 15 here? Pretty easy. Okay, so it might get a little bit harder. Here's another one, very similar problem. So we could call this one x, and so once again you can say this one x plus 17 is equal to 42. And we could subtract 17 on both sides of an equal sign. The x, of course, drops down here. Positive 17 and negative 17, of course, is 0, so this kind of subtract off. So what we have on the left side is just x. And over here, what do we have? 25, I think. Let's see, we're going to borrow one. Get 5 there. Knock one off there. I'll get 3. And get, x equals 25. So pretty easy stuff. Okay, so let's talk about congruent for a second. I mean, you may not have seen this word before. Just want to mention what it means. Congruent, oh, that's terrible. Congruent here is like the word equals. And in geometry, we say something's congruent if it has the same size and the same shape. Now, so let me just mention something. Like, so let's say we have this triangle here, and we have this triangle here. Okay. And so we might say, well, hey, those two triangles are equal. They may, maybe they look like they're equal. And they might have the same exact size. Like this might be 7, this might be 7, this might be 11, and this might be 11 here, and this might be 4, and this might be 4. So they all have like the same lengths, and they have the same angles and stuff like that. You might say, hey, they look equal. But they're not equal because one of them's blue and one of them's red. So in geometry, we use this word congruent. And congruent just means that they have the same size and same shape. So, anyhow, same size and same shape. Okay, so we use this word a lot. For practical purposes, you can think of it as meaning the same thing as equals. Now, it has a symbol. This is the symbol. It looks like an equal sign. It has a little squiggly on top. So, there's your congruent symbol. So, the point of this slide here, it makes a little bit of a difference between congruent and the equal symbol. What we say in geometry is that the lengths are equal. In other words, 8 is equal to 8. For example, you can say 8 is equal to 8. But when we're talking about the segment, we say the segments are congruent. So that just means that they have the same shape and they have the same length. So hopefully those two words won't confuse you in geometry. We're going to see this a lot more in this course, so hopefully over time you'll get more experience with this symbol and you'll have a better understanding when to use congruent instead of this one. Okay, so how can we tell whether something's congruent? Well, we can tell if they're congruent if they're the same shape and they're the same length. So what we're going to do, we want to determine whether JK, that's this segment, and LM are congruent. So let's just plot the points first. J is at -3. So 1, 2, 3, up 4, 1, 2, 3, 4. So we would put J right there. Where's K at? K is at 2, 4. 1, 2, 1, 2, 3, 4. So K is right here. So to find the length, you can just count off the coordinates here. 1, 2, 3, 4, 5. So you can say that this length here is 5. I mean, it's like, duh. Alright, well let's find, now that's a segment, so we'll try to draw a segment there. There's a segment there. Imagine it's straight. Segments are supposed to be straight. Okay, now let's draw the other segment. L is at 1, 3. So 1, 2, over 1, up 3. L is right here. And M is at 1, -2. M is right here. And this segment goes from here to here. And once again, you could just count off, you know, the length right here by just going up or down. So if we go 1, 2, 3, 4, 5, this length here is 5. So what we would say is that these segments are congruent. Now, I just want to go over a couple symbols we use in geometry to say that things are congruent. We use these tick marks like this. We'd put one tick mark here, one tick mark here. Now, that's a little bit confusing. So let me show you another diagram that will explain how this works. Let's say we have a triangle right here. Okay, that's a triangle. Imagine it's a triangle. Here's another triangle over here. And let's say that those two triangles are congruent. Well, the way we could use our tick marks, we can use like one tick mark here, one tick mark here. That would say that those two segments are congruent. And if you have more than one pair of segments and you want to say that, hey, I want to say that these are congruent, well, you can just use two tick marks. Okay, so there's two tick marks there, there's two tick marks here. And since we have a third segment, we might want to say that this segment here is congruent to this segment here. So that's how we do things in geometry. If we want to say some things in our diagram, we want to say that they're congruent, we'll just use these tick marks, just like I did here. Okay, so that's common practice. I wanted to show you that. So in any event, those two segments were congruent. And now we're up to the central question. I mean, it's that simple. Congruent segments are segments that have the same length.